Welcome, everyone. Today we have two talks related to a very new and exciting facility, the Vera Rubin Observatory, that will certainly help revolutionize our understanding of the universe in many, many areas. And today we'll hear about one. We have two speakers for you today. The first talk will be given by Meg Swan. Meg is a reader in the Astrophysics Research Centre and the School of Mathematics and Physics at Queen's University Belfast in the UK. Her research focuses on how planets and their building blocks form and evolve. And for that, she uses ground-based surveys to probe our solar system, small body reservoirs. She also serves as the co-chair of the Vera C. Rubin Observatory Legacy Survey of Space and Time Solar System Science Collaboration. Then the second talk will be given by Rosemary Dorsey, who is currently a postdoctoral researcher at the University of Helsinki in Finland. She holds a PhD in astronomy from the University of Canterbury in New Zealand, and she specializes in survey simulation, which means that she tries to quantify if small bodies will or will not be detected by solar system surveys, such as the LSST. Rosemary is particularly interested in near-Earth and interstellar objects, and she's currently also the Solar System Science Collaboration's working group lead for these research areas. With that, without further ado, Meg, the floor is yours.
Thank you. I'm going to talk about Rubin Observatory and the LSST from the community perspective. I don't work for the observatory. I co-chair the 250 or so planetary astronomers who are sort of coordinating or at least talking about how they're going to do science or preparing to do science with Rubin Observatory and the LSST. So I just want to give you that perspective of that. I will be sort of giving the community sort of perspective of where things are and what we know from what the observatory has told us publicly. So for the latest, I always recommend going to Rubin Observatory's web pages for the latest and greatest. But I'm going to give you my take on what they've been saying publicly and what the Solar System Science Collaboration has been doing. Okay, so you all know why we study solar system bodies, right? But because you're here in this webinar, but I wanted to just sort of drive the point home, right? That like the reason we study small bodies in the solar system are because we care about how the solar system formed and evolved. And these objects, right, they're from their orbits, their physical properties, tell us something about the early days of formation. And then also how the hell did we get to now, right? What are the processes that are active in the solar system today with things that are, like comets or things that have had collisions, or just, again, objects that have, changed in their dynamics, or, again, are doing odd things as we tend to know and love. And so I want to highlight that Rubin Observatory really is going to be the thing that's going to transform our understanding of small body planetary science. Because this is just going to be a discovery machine. So everything changes in a year, right? Within this year, right, and next year, a lot of things are going to change once Rubin Observatory starts the Legacy Survey of Space and Time. The expected start date is to be determined. It's coming in the coming months. They're still in the science optimization phase of sort of tweaking their image performance, and they're seeing an elasticity delivered on the camera images, but they're very, very close. So, this is coming this year. And that we'll start seeing more and more science results, and even some of the data has started already to come out, right, from the commissioning period in the next couple months, or already in the Minor Planet Center. So I really want to emphasize that point that, really Rubin Observatory will transform our view of the solar system in the next few years. And so this thing has been being built for over a decade now. And so the first stones, I think, were put down in March of 2015. So we really are at a decade of construction. And now, right, just the eve or the dawn of the start of it. And so I just want to give you some pictures to give you some scale and talk about why Rubin Observatory is amazing and will be amazing. So this is just showing you on Cerro Pachón in Chile, where this is located. So we're looking at the southern skies. And so to get sort of finding a lot of solar system objects, you need you need a big field of view, you need a depth, you need a big piece of glass, and you need to be able to do that fast. And so Rubin Observatory can do all of those things. So this is the really next generation sort of ground-based facility that's been, coming online. And so the mirror is a 8.2 2 or 8.3 meter, but because it's this unique design of the primary and tertiary mirror together to get you a wide field of view, we'll talk about it in a second, but it's about 9.6 square degrees. In focus, it needs to be a primary and secondary together. So I'm just showing you sort of the mirror with humans for scale to give you some sense. And then the camera is, strapped on to the front at prime focus. So it's not on in this picture, but it has been on for a year in commissioning observations. So Rubin Observatory is the fastest telescope. I've been told that if you had a human in the dome, you could not outrun this thing moving at full speed. So just to give you some sense of this, here's the telescope actually moving in the dome. And so this isn't quite full speed, but just to show you how fast and nimble this thing is. Most other observatories, I worked at Gemini Observatory for a few years, it is not as fast and as nimble as this. So all the technology that's gone into this system, right, is to get us to be able to cover the sky quickly with depth with a big field of view. So again, just to show you that tertiary and primary mirror designed together, here's the mirror that's been coated in silver. Just very few telescopes have to be silver, but there are good reasons in the optical properties to and reflectance to use silver. And so you can see here basically the primary mirrors on the outside and the tertiary sort of cut into the primaries on the inside. So it gets you about a 6.4 meter equivalent sort of primary mirror diameter. So if we look at sort of the scale of other observatories in that 9.6 square degrees, right, it's about 45 times the size of the full moon can be packed into that Rubin LSST field of view on LSST cam. And just to show you some of these different telescopes, right, we've had ones that have been bigger, but they've been on much smaller telescopes. And so the LSST cam on on the Monnier telescope, which is Rubin Observatory all together as a package, right, is the biggest and wide field, camera ever put on a observatory. So as I said, the camera was delivered on the summit in May of 2024. It is a technological marvel in itself. Just to give you some scale, there's humans, it's quite big. And that this thing is designed to take, observations within 30 seconds and read out within less than a minute. So, and do a 10-year survey, which we'll talk about in a second. So the LSST camera is 3,200 megapixels. Again, just to show you humans for scale, showing the CCD rafts, so the different collections of CCD detectors. And on the right, one of the engineering images, which I love, because an engineer brought in romesco broccoli and then ate that for dinner. But just, you can see the fractal patterns in here, right? Just to show you the detail in this camera itself. So if you put all together this technology, right, and the data pipelines to actually process the images that are coming off, this has been a decade-long project, not just of building these things, but working on software to be able to deliver, getting everything from the sources that are in the images, galaxies, to finding moving objects. And so Rubin Observatory is going to execute the legacy survey of space and time, the LSST. And so there are 4 science drivers. We don't care about most of them, but we care about the fact that solar system, or inventorying the solar system, is one of those 4 key drivers. So there will be probing of dark matter, there will be mapping of the Milky Way, or exploring the optical and transient sky. But the reality is that by coming back every few days, which is what the telescope system can do, right? It can image the entire visible sky within roughly 3 days. It will have in 6 filters over 10 years. So we're getting a lot of interesting things that we don't normally get with solar system. And I'll talk about that in a second when I show you sky coverage, but just to highlight that because solar system is one of these 4 science drivers, right, decisions cannot be made that would damage finding solar system objects so severely, because we are one of those 4 science drivers. And so part of what the community's job has been over these, many years, is to be advocating and ensuring that we get the maximum amount of solar system science that we can. And I can confidently say, as I've almost been co-chair now for 10 years or 8 years of the Solar System Science Collaboration, I think the solar system community has advocated, and we're getting the best survey to do solar system science once the LSST actually starts. So where is the LSST observing? It's observing mostly the southern sky. It will do the entire ecliptic. So you can see there's the entire ecliptic is locked in here. The northern ecliptic spur this region up here called NES gets the northern ecliptic. So the entire ecliptic will be observed in the LSST. The northern ecliptic spur gets a little less visits. Again, they'll be at rather higher MS, lower elevation. But on the whole, right, it means one survey with one set of systematics, one set of detections covering the entire ecliptic. So if you care about whether Planet 9 is real and you want to know if clustering of outer solar system objects is interesting, well, you're going to get the north and the south to be able to answer that. Also, everything's going to be done with difference imaging, which is not always the case when we're looking for solar system objects. A lot of surveys, me included, have done only looking for sources that have moved in images from the source catalogs themselves. And so with difference imaging, right, that's going to help a lot, especially because we're going down to 24, roughly 24.5, 24 in our magnitude. And again, right, to highlight that this is showing you the 10-year set of visits. The observatory is going to observe for 10 years. And split these observations. So you can see in the wide, fast, deep, the main part of the survey down here, in sort of the green, that you're going to get, 800 visits, but those will be divided up over 10 years and divided across 6 filters, U, G, R, I, Z, and Y. So we're going to get a lot of information about composition, right? Surface composition, light curve variability, cometary activity, and other types of activity, right, from just discovering and monitoring these objects within, the footprint. Just to give some scale of what a night on LSST would look like, this is a simulation that's a little much older, but it's in the same vein. And so each color is a different filter, and this is the scheduler that's been built for a very long time, right, that, and again, is ready to go, making all these decisions based on what the night looks like and the weather and previous sky coverage to make decisions to optimize that survey strategy that evenly supports those 4 science drivers that make up the LSST. And so, this data will be sitting there, but I think what's really exciting is that we all as a community don't have to go write our own living object pipeline, because that would be difficult to do, given it's 15 terabytes of data that are being generated at night. And so the solar system processing team led by Mary Yurch at the University of Washington is building the solar system processing pipeline that will find solar system objects and report them to the Minor Planet Center, and creating daily releases for those that have Rubin data rights, but also these discoveries will be reported to the Minor Planet Center. And so there's 2 sort of halves of that solar system processing pipeline. So one is during the day, right? So you'll take observations at night, and during the day, the software will look for new linkages of moving objects on heliocentric orbits. And so if those algorithms are able to identify objects, and again, this is a data management challenge to do this, but they are up to the task, that solar system processing team. And so those objects will be found through the daytime and sent to the Minor Planet Center. They'll get orbits, and those will get sent back to then be used at night. At night, within roughly 60 seconds after readout of the camera, then if there are any solar system sources that are predicted to be in those observations, it'll get highlighted in the transient alerts if they go, there's a transient source, and here's all the solar system objects that are close by that could be this object. And then you, as your favorite planetary astronomer doing your favorite, interest in your favorite object, can decide whether the accuracy of the orbit and the position uncertainty identify that object being the same one. So it means that in real time in the Rubin alert stream, you can be looking at cometary activity or things changing, but you can also be using the daily catalogs that get produced from the nightly search and the sort of association at night from the alerts to do your science if you have data rights. And there'll be data releases that are processing the full data with one set of pipelines or versions of the pipelines, roughly annually. So if you want to do population statistics, you probably want to use that annual catalog. If you're interested in just finding odd objects or doing specific things like cometary activity, you might want to use the daily catalogs. So I just want to highlight there's a whole bunch of people that are making this happen, particularly within Rubin. So there's an entire team of people that are building this observatory, right? From the day crew to the construction folks to those that are working on data management, the leadership. But there's also, right, I would say this core team of people that are led by Mary Yurch, who are working on getting solar system science going by working on this moving object pipeline, and working on finding basically nightly pairs of transient sources, and then linking those over three nights on a 14-day period to find new solar system objects. So this is the team that has basically gotten us ready, the community ready, by building this pipeline. So I just want to highlight, because we often don't see them very much, but this is the folks that have been spending a lot of their time to make this happen for the community. And so I want to highlight that the solar system processing pipelines will cover the entire solar system from inner Venus all the way out to about 200 AU. So roughly the distance between the nightly pairs is about 33 minutes. And so it gets you to about 200 AU where you can see motion. And again, other algorithms are being explored to see if they can push further, but that may be a community bespoke pipeline that needs to be reached to get beyond 200 AU. And so there are now simulations, I'll show you one in a second, that show how much we expect to see. And so we're looking at a wealth of discoveries coming in from Rubin. So the simulation is from Kurlander et al. And so this is using the Sorka simulator. And so J. Kurlander is including near-Earth asteroids. So these are the things in red. The yellow are the main belt asteroids. The pink are the Jupiter Trojans, and the blue are Kuiper Belt objects. And so you're seeing with every flash, right, it's a new discovery. And so we can already see by the time we get to, or at least a new observation of an object that it hadn't observed before. And so you can already see that within 2 years, we're at like 3.6 million objects, and just see how the solar system sort of fills in. And now that we're in like 2.5 years, you can notice that like sort of flashing is getting less and less. And so I'll let it run all the way to 10 years. But I want to highlight that this is using the best estimate or guesstimate of what the Rubin observing cadence is. There are simulations using the Rubin scheduler and weather models that are part of the input with the best population models. So Rosemary is going to tell you a lot more about the science and capabilities of what things you can do with Rubin data, particularly focusing, I think, on NEOs and near-Earth asteroids and interstellar objects. But I wanted to give you sort of the taste of why I think Rubin Observatory is really amazing. So we're already at like 5.2 years, right? And, we're already at 4.8 million objects. So my point is that, you really can get the sense from the scale of this. And just remember, right, it's still, this survey is still observing all the other objects, or most of them, right, over the 10 years. And so it's really amazing that we get these discoveries and we get to follow them for 10 years, which has never really happened. In most surveys, you either get enough time to find them, try to bang on the orbits to get good enough orbits right? But you never get the compositional studies, right? Because it's not built in. And so thanks to the fact that transient folks, right, that care about astrophysical transients, care about color evolution of their supernovae, and that those things have to be observed over time, right? We get those things naturally built into the survey. So we're almost at 10 years. We're nearly at 5.2 discoveries. And I just want to highlight, even though we're near the end, you still see flashing, right? Which means there still will be new discoveries of fainter objects coming more inward that were further out, that were below the flux threshold. There will be discoveries throughout those 10 years. But the highlight I want to add is that we get most of these discoveries in the first few years of the survey. And so this is a figure from J. Kurlander, just showing those same things he showed in the plot, but on the top showing the 10 years and then 0 to 2 years versus 8 to 10. And just to highlight, we're getting most of those things early. So I'll hand over to Rosemary in a second, but I just want to translate these numbers a little bit for near-Earth asteroids, main belt asteroids, centaurs, and trans-Neptunian objects. So it's about 89,000 new objects in the near-Earth asteroid population. It's about 3.7 new main belt asteroids that Rubin Observatory is expected to discover, about 1,200 new centaurs, 32,000 new trans-Neptunian objects. So if you put that in context, it's about 2.3 times the number of near-Earth asteroids found by humans to date, 2.7 times the size of the inventory of known main belt asteroids, 7 to 12 times more centaurs than currently known today, about 6 times the number of trans-Neptunian objects reported since the discovery of Pluto. And I want to just highlight that Ruben is doing some science. So there's you can read this paper by Sarah Greenstreet, which is about asteroid rotations using early commissioning data. And so the science is starting to come out. And so the observatory has released some of the observations from the commissioning survey to the Minor Planet Center. So the solar system processing pipeline is working. If you're interested, the Solar System Science Collaboration is actively getting ready for the start of the survey and advocating where we can for the needs of the community. So if you have data rights and you're interested in joining the collaboration, please do. And definitely, I think this is going to transform our view of the solar system, just from getting the data, but also all the prospects of science. So I'll stop sharing and let Rosemary tell us about all the exciting science that you'll be able to do with this large amount of discoveries and photometry and astrometry.
All right, so Meg has done a great job of giving you an overview of LSST and why, especially in the Solar System Science Collaboration, we're very excited for it to start. But for my talk, I'm going to focus on telling you about the exciting science we can do with LSST, particularly for near-Earth objects and beyond, meaning interstellar objects as well. So a little bit of motivation. What are near-Earth objects to start with? I'm not sure what our demographic of audience is, so a bit of introduction. They're objects that have evolved from the main asteroid belt for a number of reasons, and they've entered near-Earth space around the Earth. Often these are collisional fragments, and we see signatures that they're from the main belt, from different properties, including something called taxonomy, so the different classes of asteroid based on different surface compositions, different albedos, which is the amount of light that is reflected. These signatures we see in the main belt as well as in the NEOs that we observe. So the comparison here is the green histograms, which is the NBA population, and the orange, which is a debiased sample of NEOs. And they look very, very similar. And other things that tell us that these objects are from the main belt is that we see that they have similar size ratios. So the comparisons here, purple and blue are equivalent sizes. And down here for smaller NEOs, the ratio is down here. So we see signatures and evidence that these are from the main belt. Other reasons, or the reasons why we study NEOs, the first one, which is a little bit closer to home, is for planetary defense. So for example, the DART mission, which was a NASA-funded mission to test our planetary defense for potential situations in the future. So the DART mission was to use the DART spacecraft, impacted a satellite of a near-Earth object, and wanted to measure how much we could change the orbit of that asteroid, potentially deflect it from an impacting orbit with the Earth, if that was a scenario in the future. Other examples of planetary defense, the recent discovery of this asteroid 2024 YR4. And from discovery, it initially looked like the orbit might end up in the impact of this object with the Earth. This was because the uncertainty of the orbit straight after discovery was so large that there was a range of possibilities. And for comparison, the size of YR4 is approximately the size of a Boeing 767. So not a small object to be potentially hitting the Earth. Luckily, crisis averted. Thanks to JWST, we now know that this object won't hit the Earth, and in particular, the remaining uncertainty of whether or not it would hit the moon has also disappeared. But that is the reason that really highlights why NEOs are a critical population to study for real impact or real effects on the Earth, but also for the solar system. One other reason we study NEOs, or near-Earth objects, is because they're the closest and easiest things to get to. So for a comparison, on the left here is the sort of orbit and trajectory of OSIRIS-REx, which was the NASA mission to a near-Earth asteroid, Bennu. And this was a series of stages, including collecting a sample from the surface and returning it to Earth, which happened within a decade, approximately the same amount of time it took for the New Horizons spacecraft to be launched and reach Pluto. So for a comparison, a whole mission to an NEO with a sample return compared to just getting out to the outer reaches of the solar system. So these things are really very close by, relatively close by laboratories. Some results from Bennu which show that NEOs are really more fascinating than we previously knew. Recent analyses have shown that all of the nucleotide bases that make up DNA were detected as present on the surface of Bennu. I believe they didn't find DNA exactly, but all of the building blocks for life were detected with a reasonable signal strength on this object, which is very exciting for understanding how we got life on Earth today. The other thing NEOs tell us about is the interior structure of asteroids. It's very hard for us to know what exactly is going on in the middle. What is the structure? How are they built? How do they stay together while they're hurtling through space? And so these sample return missions, for example, this one, OSIRIS-REx, even just this video showing how loose and weak the surface was, which was not at all what was predicted, has changed our understanding of how asteroids formed and stay together. And lastly, another thing I wanted to highlight was the fact that these objects are very close to the Earth, and so they're a lot more affected by the sun than anything else in our solar system. And there's been some recent research which has shown that the observed population does not match the models that we have for how many objects we see with orbits reaching close to the sun. So there's evidence there that asteroid orbits or asteroids are disrupted as they get increasingly close to the sun. And if we look at distant orbits, this is the red and green lines here, there's almost no difference between low albedo or high albedo objects. And those are objects that are darker or brighter, reflect more or less light. But as we get to lower perihelion distances, we really see a difference in the composition of the objects that have those orbits. So there's something going on with the sun and the composition and morphology of these objects that we have yet to understand. So what will this look like in LSST now that we know all of the cool things that NEOs can tell us? So this is from the Kurlander paper that Meg mentioned earlier, simulating how many near-Earth objects and of what size we expect LSST to see using a survey simulation of the survey itself. So this blue line is the distribution of simulated objects, and the green is the output of LSST at the end of the 10 years. So there is a drop-off with smaller objects being harder to find, as they always are in astronomical surveys, but the sheer scale of the number of objects that we're reaching is ending up at about 10 to the 5 objects 100,000 near-Earth objects, down to even 1 meter scales expected with LSST. And so how good is LSST at finding these objects is measured by something called completeness, which is the fraction of objects of a certain size that will be found. And for objects bigger than 1 kilometer, which is a big asteroid if we're thinking about planetary defense, LSST can see about 91% of those. And for objects larger than 140 meters, LSST is able to find around about 72%. And the reason this is important is because of the US congressional mandate, the George E. Brown Near-Earth Object Survey Act, which has made it a priority for near-Earth surveys to find all of the objects, or 90% of the objects larger than 140 meters. And these things are hard to find. So LSST finding around 72% of the objects of the size is a really good step in the direction of completing this goal. The other thing with LSST, Meg showed the video of the discovery rate, how LSST will find things really quickly in the first couple of years and then slowly find more objects as it continues. And we really see this with the NEO population, which is the 3 red lines on these graphs. So as a function of, as we go through the survey, NEOs typically aren't found straight away like the other populations of TNOs or main belt asteroids. Particularly the small objects are found constantly throughout the survey. So it's really a long game. The whole survey is important for these objects and their discovery. We've already found some NEOs in LSST. So this graph on the right-hand side is from the first look data. One pointing of LSST cam for, I think, 9 or so nights across a couple of weeks. And this is from the Greenstreet et al. Paper that Meg already highlighted, showing one near-Earth object with a good enough light curve to measure the rotation period and the size of this object. The rest of these colored points are other fast rotators that were seen in the same data set. But we also have this NEO data point. And what this small sample from this one field in this very small first look data set tell us is that the interior strength and structure of main belt objects and near-Earth objects looks very different from the vast majority of data that we've already collected. And LSST is going to continue to fill this in for main belt asteroids and near-Earth objects. And for comparison here, this is roughly where Bennu lies on this plot, the near-Earth asteroid that OSIRIS-REx took the sample from. So there's a lot more exciting things to come that we can expect from the full LSST survey. So for the second half of this talk, I'm going to tell you about interstellar objects. A little bit of a jump now. These are planetesimals that have formed around other stars in the galaxy, were ejected and have been traveling throughout the Milky Way for the rest of their life. So we've seen 3 interstellar objects so far, 1 Oumuamua, 2 Borisov, and 3 Atlas. A very small population, but we're expecting that to grow with Rubin. Interstellar objects are interesting and important because we know that planet formation should be everywhere in the galaxy. We know from our own solar system that a lot of material was ejected when the planets were forming and moving around before they settled where they are today. We also know that our solar system isn't necessarily the stock standard. The planet architectures that we've seen in exoplanet surveys show a variety of structures which could influence how or what types of objects are ejected to join this interstellar object population. And we also know that there are other sort of galactic tracer properties like metallicity, composition, and age vary across time and across the physical extent of the Milky Way. So the planetesimals that we're expecting to see will be a lot of puzzle pieces locking together with all of these components. They should tell us sort of what planet system they came from, how old was it, and how metal rich is it compared to our own solar system. And before we even saw these interstellar objects, we knew they existed. There were theories, but there was also observational evidence, indirect evidence of these interstellar objects, in that white dwarfs have been observed with these absorption features of, sodium lines and potassium lines, which can't be explained by a typical white dwarf atmosphere, but can be explained by asteroids or comets falling onto the surface. So we knew these were out there before we saw the first couple. And to introduce you to our three visitors, we have One Eye Oumuamua. It was surprisingly not a comet when it turned up. We were expecting a comet, but we got One Eye, which had no coma, but it had a perturbed orbit like a comet. So that was very confusing for a lot of people. It was also very small and tumbling with a large sort of stretched shape that was highly unusual. And unfortunately, it was only discovered as it was going past the Earth on its way out of the solar system. So we only got a few weeks to observe it before it faded and we couldn't detect it anymore. 2I Borisov, the second interstellar object, was found a couple of years later. It was a comet, a little bit larger than One Eye, and because it was discovered near perihelion, just before it went too close to the sun, there was more observations able to be taken, and we got to find out more things about this object, including the composition, which looked not dissimilar to solar system comets. So that was interesting. And then our last and most recent visitor, 3I Atlas, was found last year in July. Definitely a comet, even larger than 2I Borisov. Very active with a lot of different gases and cometary species. And really importantly, it was discovered 4 months before perihelion, not days or weeks, but months, which has allowed this the planetary community to really get a good look at this object. So a little bit more about 3I, because it's the most interesting transient, in my biased opinion, to have happened in the last year. Initial observations showed that it was very red, so it was very dusty and active, even at discovery. And this right-hand picture here is actually from the LSST Rubin paper on 3I Atlas, going back through images in the Science Validation Survey. You can actually see that 3I was in the field of view on even the first night of the Science Validation Survey. So these images are available for 3I. It's had a lot of attention from some big telescopes, including HST and JWST, when it was just reaching the water ice line, where water activity typically turns on. And we did see water after this point, but at this distance, I think it was around 3.3-ish AU, you could see activity even from CO2, a little bit from CO, and a little bit from water, which are all the main drivers we see in the solar system as well. 3i even got a press tour from all the Mars spacecraft that ESA and NASA have sent over the years, including ESA's ExoMars Trace Gas Orbiter. Got a picture of 3i. And it was even spotted in the ultraviolet by NASA's MAVEN. And that's, I think, particularly special. There's not many solar system objects are bright enough in the UV to get really good images, particularly distant objects like TNOs. Uh, 3i Atlas even got spotted by the Perseverance rover. In this crosshairs here, it's a very faint streak. You can see it moving. So even got 2 birthday presents that year, as well as singing itself happy birthday. The Perseverance rover got to spot its first interstellar comet, which I think is quite nice. And then at perihelion, 3i went behind the sun as seen from Earth, which was a shame for ground-based observing, but 3i was managed to be observed by a bunch of spacecraft that particularly look at solar physics. So this was a really valuable data set. It showed that even approaching perihelion, 3i was brightening more than we expected. So this was really valuable to see. So why do we care about 3i so much? Everyone in the world was taking images of 3i whenever they possibly could. So why was it so important, this third one? And the reason why it was important, it was coming in with an unusual velocity. And this work from Hopkins et al. 2025 actually demonstrated that 3i Atlas is most likely twice as old as the solar system is, which is really quite remarkable. It's the first planetesimal we've observed close enough that it's older than the solar system. So that's really remarkable. 3i Atlas also shows this sort of unusual polarization behavior, unlike anything we've seen before for comets, and even including 2i Borisov. 3i also shows some unusual isotopic abundances. These are really rare observations. The comet has to be really bright for you to be able to get enough signal to detect these. So this was really fortunate for 3i, and the abundances that were found suggest that 3i is perhaps really old, or it's from the outer regions of the galaxy. For example, here in the work of Oppetom et al., this is the measurement for 3i in the nitrogen ratio, which doesn't look anything like the comets that we see from our solar system. So the question is, looking forward, what will LSST see of this incoming population? So this is some work that I actually did in the last couple of years, looking at the detectability of ISOs in LSST. And what we see is this northern incoming population is detected on its way in at the very top of the LSST footprint. They're discovered everywhere across the sky, and then they're last observed on their way out of the solar system. So LSST gets some reasonably good coverage of these objects as they move through the solar system. In this work, I predicted how many of these objects LSST will find, remembering that we've seen 3 in the last roughly 10 years. we calculated that LSST will find between 6 to 50 of these objects in the next 10 years. So at least doubling our discovery rate with just one survey, which is pretty astounding. And the other thing that I want to highlight, even though that sounds very impressive, is these things are going through the solar system all the time. Some of them, most of them, very, very small. And because they're passing at such huge distances, we're actually only sampling a small percentage of the actual population. But if you think about population completeness and how efficient you are at discovering these things, the efficiency here is less than 10 to the minus 4%. So these things are very, very hard to find. The fact that LSST will find at least 6 of them is amazing in my mind. And the reason why this is such a wide range of estimates is a number two main things that are still really uncertain for the interstellar object population. There's the absolute magnitude distribution, which depends on the size of the objects. We really have no firm understanding of what this should be. We have models for planet formation, and we have models of the size distribution of solar system objects, but we don't have a concrete idea of how those piece together. And then on the other hand, we don't know how many of these objects are out there in the galaxy. How much stuff does each star produce that will inform this? So while we think it'll be somewhere between 6 and 51, the number could be a little bit different. But that will tell us something interesting as well. What we see with LSST is for different size distributions from shallower to steeper, we see a difference in the distribution of sizes that LSST will find, which sounds very intuitive. We will see a difference in, for example, the mean or the median absolute magnitude of the objects that LSST will see. And this actually demonstrates why 3I was so exciting at discovery, assuming that it was an asteroid and not a comet, which it turned out very quickly that it was a comet. The size of 3I indicates some really interesting constraints on the size distribution of ISOs. In comparison, 1I, Oumuamua, a lot smaller, actually, if discovered by LSST, doesn't tell you very, very much about the population. So this was one of the reasons why 3I was so exciting at discovery. So in the pessimistic case, with 6 ISOs, you think that's a little bit disappointing. Even with that number, we will be able to say something about the size distribution. And in the optimistic case, we'll have 51. We'll have even more information. But the encompassing thing here is that the ISOs and LSST will give us some clues about what the intrinsic population looks like. One small drawback for LSST is that it is a southern hemisphere telescope, and this is a population coming in from the north. So we will see some biases in the objects that it discovers. So this plot on the left here just shows you the bias in the orientations of the orbits. And this just simply says most of the objects that LSST will find will have perihelia in the southern hemisphere, which is what we expect for a southern telescope. It also means that ISOs are not going to be found pre-perihelion, or not mostly pre-perihelion as we possibly hoped. But they will be found around perihelion, and about half of them will be found beforehand, which is still really good going for a population that we know very little about. So we will get some good warning for these objects as they're approaching perihelion. And this is one of the reasons why this pre-perihelion discovery is important. So this is a plot of how many days an ISO will spend brighter than, for example, 23rd magnitude, which is sort of the limit for spectroscopic studies, which are very important for understanding things like the composition of an ISO. And for about 50% of ISOs, they will be observable in LSST for 120 days or longer. So that's 4 months of observing and follow-up that LSST and other surveys will get of these objects, which is really exciting to think about. And so this is sort of the summary of what I would like you to remember about NEOs and ISOs in LSST, is that LSST is going to probe the smallest of fastest objects and tell us a lot more than we already know about their evolution, their internal structure, and how they might evolve and self-destruct almost at the end of their lifetimes. And regarding the galaxy, even in a planetary science perspective, we are going to find some things out about the size distribution and chemistry of the interstellar objects that are in our galaxy. So those are some really, really exciting results that a lot of people are looking forward to with LSST. And I'll stop there.
Thank you so much, Rosemary. Thank you so much, Mag, for these wonderful, very informative talks. We have a few questions already lined up here, so let's go straight to the questions. We have another 15 minutes scheduled for our session. So the first question is by Warren. Warren asks, you mentioned new detections being communicated to the NPC. Will Rubin asteroid detections of previously known targets be used to improve those orbital ephemerides?
Yeah, I can take that one.
Yeah.
Yeah, absolutely. So one of the really nice things is that Rubin astrometry is all tied to Gaia, at least, for the next few years, that, frame will hold and being very, very accurate. And so, yes, all observations of solar system objects will get into the Minor Planet Center. And so my understanding is for the trans-Neptunian objects that with LSST observations, it almost instantaneously takes all known TNOs that get observed by Rubin that have, were previously discovered. They'll be good enough orbits that you could predict stellar occultation events, which help us get size for these bodies. So absolutely, that all that information will be sent to the Minor Planet Center, not only for new discoveries, but for other detections. And also, who discovers what is a very complicated matrix within the Minor Planet Center and IAU. So Rubin might see something, discover things or recover things that have been lost, or sitting in what's called the isolated tracklet file within the Minor Planet Center, where things have been submitted and they're one night, but it doesn't mean we have a very good orbit at all. So on both those sides, Rubin's going to really transform, I think, what we're going to know. It's one of and also the Minor Planet Centers had to do a lot of work just to deal with that data deluge. They're ready. They've actually, been testing as they go with the Rubin Observatory. So that's why some of the early data is out, is to make sure the Minor Planet Center doesn't get overwhelmed on day one of the survey. So great question.
And there is an associated question from another attendee who wants to remain anonymous. How will we know which of the NPC asteroids are discovered by LSST? Is there a tag, maybe?
So discovery happens by the Minor Planet Center and International Astronomical Union. It technically comes when the object gets numbered, when it has a very secure orbit. So you don't really know until that moment whether Rubin Observatory or Panzers or something else conveys that discovery. I know that the observatory will be looking at sort of metrics of what they think will eventually happen, because it's a good number to know. But that's the tricky bit of that, when you submit a solar system object, it's only till it's numbered do they actually designate who the actual discoverer is. And so, other observations can come in, but it couldn't be released, and all these things. And so there's lots of documentation on the Minor Planet Center website of how they fill that out. But I think either way, Rubin's going to find a huge number of objects. So I'm not worried that discovery credit's going to be, the observatory is not going to get discovery credit for things. It's going to be well known as a recovery and a discovery machine, I think, the way to think about it.
Excellent. There's a couple more questions. Colin, you want to take one?
Certainly, yes, thank you. So Nicole asks, will the obtained LSST data be accessible for students without direct survey membership to work on meaningful projects? And are there research directions that are suitable for master's level projects?
Rosemary, do you want to take this one?
Sure. So regarding access to data, I believe generally you have to be associated with, for example, a university which has an agreement with LSST, sort of what's called like an in-kind contribution, which then in exchange that university gets data rights to the data. I think there might be avenues if you're not affiliated to get data access. The best way to do that would be to contact the science collaboration associated with your particular research interest and reach out and see what they can do. Regarding science projects for students, I mean, LST is just there's going to be so much data, no one's going to know what to do with it. So I think there's availability for any sort of research project of whatever scale. And the interesting thing will be a lot of the data comes in initially in the first few years of LSST. We're going to have so much data for so many projects, they're not all going to be able to get done at once. So the more the merrier is sort of the key takeaway there.
Thanks, Rosemary. We have another question from Hakan. Hakan asks, why do the ISOs come in mostly from the north?
That's a good question. Actually, I realized I didn't cover that. The solar system moves through the galaxy in and out of the galactic plane where most things orbit. And currently, the sun is moving in a direction such that it's moving through the galaxy in a way that ISOs come in from a point in the northern hemisphere. So we mostly see them coming from that direction. They can come from all around us, but it's sort of like if you imagine sort of running through the rain, the solar system is sort of running into these ISOs as it moves through the galaxy.
Like the radiant point for meteor showers.
Yeah, exactly. Yeah.
Would you like to take the next couple, Martin?
Yeah, sure. So we have two more questions at this point. Masoom asks, how does Rubin observations are safeguarded from LEO satellites? Do we get streaks in survey images? With 1 million satellites out there, yeah.
I can take that one. So obviously the vermin of the sky are there. Big field of view with a small percentage taken out, it's still a big field of view. So there are streaks. There are data management algorithms that have been implemented that identify those and pull them out before the transient pipelines and solar system pipelines run. So it's not as bad of an impact because of that. It's worse at twilight. So Ruben will look for objects inward of Venus. That is going to be more impacted in those observations. And again, there's discussions, I guess, with those in general with those companies about how they can maneuver such that there's less glinting. During the night, it's better. It's mainly twilight where there's a lot more impact. But the simulations that have been done at least show that you can still get a lot of data. It does take a percentage out of your pixels, but at least for now, there's still lots in that field of view that's there. But yeah, there's already algorithms that are built now to take out those streaks. So yeah, they won't be sitting in the solar system objects hiding as a fake solar system object. They'll be already removed.
Okay, I hope that answers the question. We have a webinar about this topic, about space pollution, or LEO pollution of our skies, by the way, coming up in July. Then Simon asks, do we know when the LSST new observations will become available on the NPC? Will this be updated daily or weekly?
So I'm
Hourly?
going to give, I can answer this
Secondly?
one. Yeah, I can answer this one.
Yes.
So the aim is that they would be there, that observation we sent to the Minor Planet Center, during the day, before, and then the Minor Planet Center would have time to process those and get it back. That's the ideal. You have to remember this observatory is still being commissioned. So the first year is going to be bumpy, as any big system that's taking data. These are the first time those pipelines are running at that scale on everything. So the solar system processing team is getting up and running to that point. Data is in the Minor Planet Center. So again, if it's in the Minor Planet Center, it is public. You can grab it. But just want to highlight they're getting up to the point of doing it daily, because this is the first time that their pipelines are being run on scale, right? Or will be. So there's science optimization, which is the current stage. It's really, that the observatory is in the last stage before they go into the survey. It's doing sort of now a set of observations. So it'll be a little bit bumpy, but the aim is that once they get to steady state, right, give the team a couple months to sleep, right, see how things are going. But the idea is that those observations should be in the Minor Planet Center by that afternoon, and then that Minor Planet Center has the afternoon to get it back, so that new orbits can be calculated for the evening for the association part of the pipeline. So they're getting there, and that's why you're starting to see some observations in the Minor Planet Center, because baby steps, right? They want to start processing, getting some data out, break the Minor Planet Center's pipelines, right? Break their own pipelines. So these are all good signs that the fact that they've released 11,000 asteroids and TNOs from the science validation and commissioning observations from last year. That's already a good sign that the solar system processing team is on the right track.
That's amazing. Sounds like going to be Christmas every day for 10 years or so. I don't see any more questions from the audience at this point. We still have a little time if there's questions. I have one, actually two. One for Rosemary. So you talked about the age distribution. Why would the age distribution of ISOs, why would it be different from our solar system?
Yeah, that's a good question. I mean, even within our solar system, we see a range of distributions across different populations. The TNOs look different from main belt asteroids, which look different from the Jupiter Trojans. And it all is due to the different processes they've undergone, how they formed, and then how they've evolved throughout the 4.5 gig years the solar system has been around. So we see this diversity across our own solar system, and then we know that there is a diversity of solar systems within the galaxy. So, we don't know how big the relative contributions are from, for example, trans-Neptunian objects in another star. So it's a complicated jigsaw that we don't really have any constraints on at the moment, but we're hoping the next lot of discoveries will help with that.
Exactly. I imagine that from a starting point, you could assume it's the same as the solar system.
Yes,
The
exactly.
only thing you can really do, I guess.
Yes, yeah. I mean, all of the simulations we ran were with just simple power laws, because that's how we see the physics playing out in our own solar system. But the exact details that we see for our own solar system won't come for ISOs until much later, until we have more and more discoveries. So the rough physics should be the same, but we want to know exactly all the details, which will take a while.
Sure. Thanks. And then any more other questions from the audience? Because I've got one more, if I may. Callum, am I allowed?
You can have one more, Martin.
Okay. So 10 years LSST, 10 years after that, what we put it on the moon? Why 10 years? What's this facility should be going for a century, I guess, right?
Well, the observatory is going to be, but the LSST is 10 years. So yeah, they're obviously not going to no aid funding agency is going to build this thing and let it go, right? I mean, Gemini Observatory, the VLT, they're all like 25 years, right? So the observatory is going to be there. What's going to happen next, I think, is a different question. First, there's already started to be discussion of that. There's a workshop, I think, in Stanford in August. It's like, what happens after the LSST?
Right.
I think you got to get
extended
into
mission,
the LSST
extended
first.
mission, yes.
But yeah, I think the camera's probably not going anywhere. But first we got to get into the survey, and then then something else happens.
Sure.
But I would imagine that the camera and the observatory, as long as they're all working, will continue well beyond. And so it's just going to have a different mission. And so whether that's a dedicated solar system survey or dedicated ISO survey that is doing a different survey, and strategy, I think that's to come. But first we got to see what we get. And so,
exactly.
Think of it as this way, as this is the first 10 years. What the next 10 years of this observatory, we don't know yet, because we first got to see what we get.
Exactly what we get, and then that will also decide how we go forward. Thank you. Okay, excellent. So I think we are more or less on the hour. Any more? Okay, we could host one more question from the audience if there is any. Otherwise, what do you think, Callum?
I think that probably is a good point to close out. We are perfectly to time. Thank you, everybody, so much for joining us. As I've just posted in the chat, our next webinar session is on the 23rd of June. It's going to be about accessible conferencing with Stenkelder from Bira in Belgium. Really excited for the session. I think it's a really important topic and something that we'll all really profit from being more aware of. So I do invite you to join us for that. I've just put the registration link in the chat, so do please check that out. And I hope we'll see you then in 3 weeks' time.
Excellent. Thank you so much, Meg. Thanks to us, Rosemary, everyone who attended. Have a great day.
See you all soon. Bye-bye.